Hello everyone. Welcome back to my course Aerospace Engineering, Basics of Aerodynamics. In this video, we will talk about glider flight, forces, glide angle, and trajectory. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. What is a glider? A glider is a special kind of aircraft that has no engine. Paper airplanes are the most obvious example, but gliders come a wide range of sizes. Toy gliders, made of balsa wood or styrofoam, are an excellent way for students to study the basics of aerodynamics. The Wright brothers perfected the design of the first airplane and gained piloting experience through a series of glider flights. These aircraft were similar to modern hang gliders and were launched by running off a hill. More sophisticated gliders are launched by ground-based catapults or are towed aloft by a powered aircraft, then cut free to glide for long distances and for a long period of time before landing. The space shuttle flies as a glider during re-entry and landing. The rocket engines are used only during liftoff. 3 forces on a glider. Compared to a powered aircraft, we see that a glider has only 3 main forces acting on it: lift, drag, and weight. As before, we have collected all of the component forces together and represent them by single forces acting through the center of gravity or the center of pressure. Because gliders carry no fuel or engines, they are usually lighter and simpler than powered aircraft. In order for a glider to fly, it must generate lift to oppose its weight. To generate lift, the glider must move through the air. But the motion of the glider through the air generates drag. In a powered aircraft, the thrust from the engine opposes drag. The glider, however, has no engine to generate thrust. With the drag unopposed, the glider quickly slows down until it can no longer generate enough lift to oppose the weight. So how does a glider generate the velocity needed for flight? The simple answer is that a glider works by converting altitude into speed. As it moves from a higher altitude to a lower one, it gives up some of its potential energy, and that lost potential energy becomes kinetic energy, which shows up as velocity. This exchange is always happening, which is why a glider is constantly descending relative to the air around it. Even when it appears to be moving forward smoothly, it is still gradually losing height in order to maintain the speed required to keep flying. How do gliders stay aloft for hours if they constantly descend? Gliders are built to be extremely efficient, which allows them to descend at a very slow rate. Because of this slow descent, a pilot who finds a column of air rising faster than the glider is sinking can actually make the aircraft climb, increasing its altitude and therefore its potential energy. These rising columns of air are known as updrafts. One common source of updrafts occurs when wind encounters a hill or mountain and is forced upward as it moves over the terrain, creating a natural lift on the windward side. However, once the wind passes the peak and moves down the opposite slope, the air may drop rapidly, forming a downdraft, which pilots must be careful to avoid. Updrafts also form over areas of dark ground that absorb more sunlight than lighter surfaces. As the sun heats these darker land masses, the warm ground in turn heats the air directly above it. When the air becomes hot enough, it begins to rise in a vertical column. These rising columns of warm air are called thermals. Many large gliding birds, such as hawks and owls, rely on thermals to gain altitude without expending energy by flapping their wings. They circle within the thermal, allowing the rising air to lift them higher. Gliders can use the very same technique, circling within these rising columns of warm air to climb efficiently and maintain flight without an engine. Updrafts and downdrafts. One of the early challenges in learning aerodynamics is understanding relative velocity, how motion looks different depending on the frame of reference you choose. Aerodynamic forces arise when an object moves through the air, but the air itself can also be in motion. Because these forces depend on the square of the velocity between the object and the air, it is important to define velocity in a clear, consistent way. To do this, we choose a fixed reference point and measure all motion relative to it. In this case, the reference point is on the ground, which allows us to describe both the motion of the glider and the motion of the air with respect to that fixed point. Although air can move in all three dimensions, here we focus only on air motion that is vertical, perpendicular to the ground. Horizontal wind components, which affect the aircraft along its flight path, are considered separately. On this slide, the glider travels through the air along a specific flight path with a certain velocity known as the airspeed. The flight path itself is inclined at an angle relative to the horizontal, and this angle is called the glide angle. Because the airspeed is a vector, we can break it down into two components, a horizontal component and a vertical component. The forces acting on the glider behave similarly. Drag acts along the flight path in the same direction as the airspeed, while lift acts perpendicular to the flight path. Importantly, the lift generated by the wings depends solely on the airspeed, not on the glide angle. The air also has its own vertical motion, described by a quantity called the wind speed. Since this wind speed is a vector, it can point upward or downward. Positive vertical motion is referred to as an updraft, while negative vertical motion is called a downdraft. The vertical motion of the glider relative to the ground is the vector sum of two quantities, its vertical airspeed and the vertical wind speed. If an updraft is rising faster than the glider is descending through the air, then the glider will gain altitude, even though it is always sinking relative to the air around it. In contrast, a strong downdraft can force a glider to lose altitude even when it is climbing relative to the surrounding air. Updrafts appear in a few common ways. One source is wind striking the face of a hill or mountain and being forced upward as it flows over the terrain. Pilots must be cautious, however, because once the air passes the peak, it may descend sharply on the other side, forming a downdraft. Updrafts can also be created by solar heating. When the sun warms the ground, the heated surface warms the air immediately above it. As that air becomes hotter and lighter, it begins to rise, forming a column of warm, rising air called a thermal. All of the explanations on this slide refer to what is known as static performance. In other words, the wind is assumed to be steady, and the aircraft is assumed to be aligned with its flight path. If the wind becomes unsteady, if an updraft or downdraft changes suddenly, it can momentarily alter the aircraft's angle of attack and produce additional forces. The same is true when the pilot maneuvers the glider along its flight path by adjusting the elevator. These more complex, unsteady effects are beyond the scope of this particular explanation. Glide angle. When a glider descends steadily, meaning its velocity remains constant and it experiences no acceleration, it continually loses altitude as it moves forward. In this situation, the glider follows a straight flight path, represented by the sloping red line in the figure. This line eventually meets the ground at an angle labeled A, known as the glide angle. If we know how far the glider travels horizontally and how much altitude it loses during that time, we can determine the glide angle using basic trigonometry. Specifically, the tangent of the glide angle is equal to the change in height, h, divided by the distance flown horizontally, d. Once the glide angle is known, the same relationship can be used to predict how far the glider will travel for a chosen loss in altitude. A small glide angle means the glider covers a large horizontal distance for every unit of height lost. This is the kind of performance associated with efficient gliders. On the other hand, if the glide angle is large, the glider will travel only a short distance before descending the same amount. In this sense, the glide angle serves as a clear indicator of how efficiently the glider is flying. As explained elsewhere, the glide angle is directly tied to the lift-to-drag ratio. A smaller glide angle corresponds to a higher lift-to-drag ratio, which is the hallmark of good aerodynamic performance. Vector balance of forces for a glider. This slide illustrates how the forces acting on a descending glider balance one another. A thin horizontal red line is drawn parallel to the ground through the glider's center of gravity, and a second thin red line represents the flight path, which slopes downward to the left. The angle between these two lines is labeled A, and this angle is known as the glide angle. It is the key geometric relationship that links the glider's path through the air to the forces acting on it. The weight of the glider, represented by the symbol W, acts straight downward toward the center of the Earth. Because the horizontal red line is drawn parallel to the ground, the weight vector is perpendicular to this line. Drag, identified as D, acts along the sloping flight path but in the opposite direction of motion, resisting the glider's movement. Lift, labeled L, acts perpendicular to the flight path. Using basic angle relationships for parallel and perpendicular lines, the glide angle A appears not only between the flight path and the horizontal, but also between the lift vector and the vertical direction, and between the drag vector and the horizontal direction. This makes it possible to break lift and drag into vertical and horizontal components using trigonometry. When the glider is not accelerating, its forces must balance. In the vertical direction, the total upward force must equal the total downward force, so the weight equals the vertical components of lift and drag. This gives the relationship. Weight equals lift times the cosine of the glide angle plus drag times the sine of the glide angle. In the horizontal direction, the horizontal component of lift must balance the horizontal component of drag. So the equation is lift times the sine of the glide angle equals drag times the cosine of the glide angle. Rearranging the horizontal equation yields the lift-to-drag ratio equals the cosine of the glide angle divided by the sine of the glide angle. This ratio of trigonometric functions is the cotangent of the glide angle, which is also the reciprocal of the tangent of the glide angle. For small glide angles, typical of efficient gliders, the tangent of the angle is nearly equal to the angle expressed in radians. This means that the lift-to-drag ratio is approximately equal to the inverse of the glide angle for small angles. This relationship has practical value in aircraft design because the lift-to-drag ratio is a direct measure of aerodynamic efficiency. From the equations, A higher lift-to-drag ratio corresponds to a smaller glide angle. The glide angle determines how far a glider can travel horizontally for every unit of altitude it loses. A small glide angle allows the glider to cover a long horizontal distance while descending only a little. For this reason, designers seeking to build gliders that can travel long distances focus on achieving a high lift-to-drag ratio. Conversely, by measuring a glider's glide angle and knowing its weight, we can work backward to determine its lift-to-drag ratio, as explained on another slide. Glider trajectory problem. When we consider the vector balance of forces acting on a glider in steady flight, we arrive at two key relationships. The first is that the lift multiplied by the cosine of the glide angle plus the drag multiplied by the sine of the glide angle must equal the weight of the glider. The second is that the lift multiplied by the sine of the glide angle must equal the drag multiplied by the cosine of the glide angle. Together with the trigonometric equation for the glide angle, these give us three equations that allow the lift and drag of a glider to be determined experimentally. By test flying a simple glider, such as a paper airplane, and measuring both the horizontal distance flown and the height from which it is released, we can calculate the glide angle using the first equation. Once the glide angle is known, and with the weight of the glider measured beforehand, the remaining two equations contain only two unknowns, lift and drag. Solving these equations gives average values for the lift and drag forces the glider experienced during the flight, providing a practical way to study aerodynamic behavior using straightforward observations and calculations. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. How does a glider primarily generate the speed needed for flight? The correct answer is by converting altitude into kinetic energy. Question 2. What are thermals in the context of glider flight? The correct answer is rising columns of warm air created by the sun heating the ground. Question 3. What does the glide angle of a glider represent? The correct answer is the angle between the flight path and the horizontal ground. Question 4. What happens to a glider when it encounters a strong downdraft? The correct answer is it loses altitude even while climbing relative to surrounding air. Question 5. What does a small glide angle indicate about a glider's performance? The correct answer is it can travel a long horizontal distance for a small altitude loss. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, You'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with aerospace engineering, aerodynamics, and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about Newton's laws of motion. See you in the next video. Bye.